Right. So what we're going to do is we're going to start with angular momentum. Yeah, we'll be going a little over probably. It depends. We're going to start with the angular momentum or continuing conservation of angular momentum, and then we'll move on to a different subject. So let's talk about off-center collisions. So what we saw last time is that there are some problems where angular momentum conservation is really handy. It will help you solve them. But in principle, you could solve them without angular momentum, and you could just use translational momentum probably. However, there are some problems that you need to use angular momentum conservation. You can't use translational momentum conservation just because translational momentum is not conserved in some of these problems, whereas angular momentum is conserved. So these would be cases where there is some external force which would ruin translational momentum conservation, but there are no external torques, and that can happen for a variety of reasons. But I'm going to give the simplest example where this happens, and this is the ballistic pendulum with a rod. So the standard ballistic pendulum is just like a mass tied to a mass, or like an object tied to a massless string. And you can treat the hanging object as a point mass. But here, the situation is entirely different. You have a physical extended rod hanging from the ceiling, say with mass m2, and a bullet hits it at the bottom with mass m1, and maybe the bullet is moving at some speed vi. Let's say that the pendulum has length L. Then, at a later time, the bullet enters the rod, and then they start swinging together, right? So here we have M1 again, we have M2 again, and now the whole thing is moving together at some speed Vf. So let's first try to figure out why we can't use translational momentum conservation here. So let's be extra careful. So imagine for a moment, so what do we need to happen in order to have translational momentum conservation? Well, we have to have that the net force, or rather the net external forces, are zero, or at least the net external forces in the directions we care about are zero. In the standard ballistic pendulum, we don't care about the vertical forces. We ignore those because they don't really affect the horizontal motion at all. So let's just look at what possible horizontal forces there are. So looking at the rod, just the rod alone without the bullet, there's going to be two forces on the rod, right? There's going to be the force of the bullet on the rod when it's entering the rod, but there's also going to be the force from the hinge on the rod. And one way to see this is that, think about it this way. If there was no horizontal force from the hinge on the rod, then when the bullet entered the rod, the whole thing would just move to the right. But it doesn't, and that's because there has to be a counterforce, basically, it's almost like a normal force, from the hinge on the rod. Think about it, yeah, that's the easiest way to see it. Because if there was only one force on the rod, let me just draw a free body diagram. If there was just a force this way, the whole system would move to the right. So you need another force that's pointing some other direction. Otherwise, even the top part of the rod would move to the right. No, it's not friction. It's really just like it's just a normal force. It's like if you think of what a hinge is, it's just like the bolt of the hinge pressing up against the socket of the hinge. That's all. It's just another normal force. But the point is there is an external force that's not coming from the bullet that is acting on the system being the rod bullet system. So because there's another horizontal force, an external horizontal force, we lose the fact that we lose the angular moment or the translational momentum conservation in the horizontal direction. That is, in this case, the change in the momentum, the center of mass momentum in the x direction is not zero. So you can't say that the initial momentum in the x direction is equal to the final momentum in the x direction. It's just not true anymore. However, what we can do is we can look at torques. So if we use the hinge as a pivot point, then we can think about what forces produce what torques. The hinge forces, the forces that come from the hinge being attached to the rod, this is the horizontal force, and also the vertical force that keeps the rod from falling down. The hinge forces produce no torque because they are located at the pivot point. That is, that the vector r in r cross f is 0. The gravitational force also does no torque, and that's just because the gravitational force is straight down from the pivot, and so the vector r crossed with the gravitational force is 0. The torque due to gravity is also 0. So that is, there are just no external torques. Which means that angular momentum is conserved. That delta L is equal to 0. So we can use angular momentum conservation, that the initial angular momentum is equal to the final angular momentum, and that will still be valid and will let us solve this problem. So let's figure out what the initial angular momentum is. So the initial angular momentum is just the angular momentum of the bullet before it hits the rod, because the rod's not moving. And so to find that, we just treat the bullet like a point mass. So there's a pivot here, and then there's a point mass moving with some speed this way. Well, that angular momentum is the translational momentum times this distance, this perpendicular distance. In that case, this distance is L. It's the distance between the pivot point at the hinge and the bottom of the rod. So here, the initial angular momentum of the system is just the initial angular momentum of the bullet. So this is just m1 times vi times L. Now, what about the final angular momentum? Well, it would be the final angular momentum of the bullet plus the final angular momentum of the rod. So the final angular momentum of the bullet is just, well, however fast the bottom part of the rod is moving, that's how fast the bullet is moving. And then we can use the same logic to find the angular, am I recording? Yeah, we can use the same logic to find the angular momentum of the bullet after the collision. So this would just be m1 vf times L. Then we have to add to it the angular momentum of the rod. Now this is the angular momentum of just the rod, not including the bullet. And so we have to think about what the angular momentum of the rod is about this pivot point. Well, we know that for any rod, this is not necessarily a uniform rod. For any rod, well, let me rephrase. So the angular momentum of a rigid body that's rotating, because the rod is going to swing up, it's going to rotate about that axis, is just I times omega. Now the I is the moment of inertia about the hinge times omega, where omega is the angular speed. Now we can simplify this a little bit because the angular speed is related to the velocity at the bottom of the rod, right? This is just the standard relationship between translational and angular speed. So in this case, the angular speed is related to v final through the length. And that should be fairly clear. If it takes 1 second to go, if it would take one, why both r of the bullet is L, shouldn't it be r sin theta? No. So this is before it swings up. This is right after the collision. The rod is still in the vertical position, but it's now it's moving. Right. So if the bullet, or if the bottom part of the rod was sufficiently fast that it would, in principle, make a full revolution in 1 second, then the angular velocity would just be 2 pi radians per second. But a full revolution is 2 pi r, and that r here is L. It's the same justification that we typically use. So we can substitute this in. We get m1 vf times L plus I hinge times vf over L. Okay. Now, so we can use angular momentum conservation to set these two things equal to each other. So we have that m1 VIL equals m1 VFL plus moment of inertia of the rod about the hinge times VF over L. And we could rewrite this, we could factor and simplify. But before we do that, let's figure out what this is. So I don't, in principle, know what the moment of inertia of the rod is, especially if it's not uniform. If it was a uniform rod, then it would be 1/3 ml squared, or m2 l squared, right? because that's the moment of inertia of a uniform rod about one end. But if it's not uniform, then the moment of inertia could just be something else. We know that it will depend both on the mass of the rod and on the length of the rod, but we don't know if it'll be a third or 1/19 or 2.5 or whatever. In general, it'll just be, say, beta I hinge is beta times m2 L squared. And so depending on how the mass is distributed throughout the rod, this will tell us how this will affect the number beta. Beta is just a number here. For a uniform rod, beta is 1/3. For a quadratically varying rod, it would be some different number, but it's just a number. And I just don't want to work with any particular example right now, and we can plug things in at the end when we want to check our answers. So let me just fix this. So if the rod is uniform, beta is 1/3. Right, so then we can just solve for VF. VF, using this equation and plugging in what I hinge is just m1 divided by m1 plus beta m2 times VI. And there's our answer. And so we can just check. We could try seeing what we get when we plug in beta as 1/3 for a uniform rod. You would get that it's 3/4 times the initial velocity. It just is what it is. That's how fast the bottom would be swinging if this was a uniform rod. So let's just go back and double check that the translational momentum of the system isn't conserved, because I told you it was, and I gave some reason, but maybe you doubt me. So we can actually just check. We're going to check that the center of mass translational momentum in the x direction is not conserved. So let's write down the initial translational momentum. It's just m1 times VI, because only the bullet is moving, right? It's just the momentum of the bullet. Sorry, we're doing this anyway. So this would be m1 VI. And then the final translational momentum in the x direction would be m1 times VF. And then we'd have to figure out what is the translational momentum of the rod. Well, it would just be the mass of the rod times the center of mass velocity of the rod. But the center of mass velocity of the rod depends on where the center of mass is. Like if the center of mass was halfway up, for example, then however fast VF was, the center of mass would be half as fast. If it was 1/3 of the way up, the center of mass would be moving at 1/3 of the speed, and so on. So what I'm actually going to do is I'm going to label the center of mass. I'm just going to imagine that it's here. And we're going to call this distance here, we're going to call it alpha times L. And then this distance, let me put m2 over here. This distance would be 1 minus alpha times L. So alpha just tells us where the center of mass is. So if for example, if the rod was uniform, then alpha would be 1/2, because the center of mass would be halfway down the rod. If there was more mass closer to the top of the rod, then alpha would be smaller. If there's more mass closer to the end of the rod, alpha would be bigger. So alpha is just some number between 0 and 1. Right. So VCM in this case is equal to alpha times VF. Alpha is not angular acceleration. Oh, let me use a different variable. Sorry, I just like using Greek variables. Let's use, no, A is taken, B is taken. Let's use B. B is not taken. So this would be 1 minus B. So hopefully you guys can follow why, if the center of mass is halfway through, so if the center of mass is halfway down the rod, then the center of mass of the rod would be swinging at precisely half the rate that the bottom of the rod would be swinging at. So in this case, the center of mass velocity is just B times the speed at the bottom of the rod, which is VF. So we can just plug that in. And so we can write that PF is just M1 plus, not alpha, plus BM2. And now I'm going to substitute in what VF is, times M1 over M1 plus beta M2 times VI. So now let's just check. So we know what the initial translational momentum is. We know what the final translational momentum is. So let's just check if they're equal. And we can do that by checking an example. So we're going to do the simplest example where M1 and M2 are the same. They're both M. And the rod is uniform. if the rod is uniform, then that means that B is equal to a half. The center of mass is halfway down the rod, and beta is equal to a third. That is, the moment of inertia about the hinge is 1/3 ml squared. So we can plug that in, and we get that PF is equal to 9/8 times M1 VI, which is not, in particular, equal to PI, which is to say that in this particular scenario, the initial translational momentum is different from the final translational momentum. And that'll be true for all of these, regardless of which rod configuration you chose. That'll just be true. So fine, we have to use angular momentum conservation here. It turns out that there are also cases where you have to use both. And that's going to be the last topic of angular momentum that we talk about. So this is, what did I title this? I titled this off-center collisions, but really that should have been like, oh boy, I'm just going to reuse the same title. So really, we're going to talk about off-center collisions now. That was technically an off-center collision. We're going to talk about true off-center collisions here, though. So in this example that I just did, there was an external force, right? And that external force was from the pivot and from gravity. But if we took the pivot point away, if we took gravity away, then we just have a collision with a bullet or we just have a collision between a bullet and a rod. The rod is floating in space. There's no gravity. There's nothing attached to it, and it just hits a bullet. So the bullet just hits the rod while they're both floating in space. And so what would you expect to happen? Well, you have your rod, you have your bullet, comes in, hits it at the bottom. Maybe you expect like it moves forward a little bit, it spins, and so on. So we can actually analyze this scenario. We can ask how far does it move, how quickly does it rotate, and so on. We can actually do that analysis. That's what we're going to do here. So it turns out that we also have to use angular momentum conservation for this complicated situation. But we have to make sure that we are being very careful to use the same reference point before and after the collision, because the object's going to move, right? So we have to make sure that we're being consistent, or rather the object will start spinning. So we have to make sure that we're being consistent with regards to the reference point. So just as a quick word of caution, I'll write that down. Reference points must always stay in the same place. They must be in the same place before and after the collision. That's true, and that's just for angular momentum conservation. I mean, that's true in general. You should always be consistent with your reference point choice. But so in this case, with no gravity and no hinge, we have two conservations now. We have angular momentum conservation and translational momentum conservation, because there's no external forces and there's no external torques. So we can use both, and it turns out that we will need to use both. So let's just do it and see what happens. So we're going to start with our rod, say oriented this way. It's the same rod. It has some mass distributed some way. It's stationary. Bullet comes in with some speed VI, right? And again, we're going to call the center of mass, center of mass is over here. We're also going to choose the center of mass to be the pivot this time, just because it's a little bit more intuitive what happens. Again, the whole thing is length L. This distance to the center of mass from the top, we'll call that, again, BL, and this distance will be 1 minus BL. Okay. And then after the collision, so this is before, after the collision, the instant after the collision, so before it's actually started moving, but it has a velocity, bullets lodged in here. We have our center of mass still. Our center of mass now has some velocity, called that VF. This is the pivot. Again, this distance is 1 minus B times L. But now, also, the whole thing is rotating about that center of mass, as well as moving. So it's both spinning and it's moving, right? And we'll call the rate at which it's spinning omega. Now, the motion of the center of mass is not necessarily related to the, I mean, it's related, but only in a roundabout way. to the angular velocity, right? You could imagine that it spins really fast, but doesn't move very fast. Or you can imagine that it moves really fast, but spins very slowly, right? It depends on the situation. So now we just have to do the analysis, this time using two energy conservation, or two momentum conservations. So just as a quick aside before we continue, we're certainly going to need the speed of the bullet after the collision. In terms of the variables that we've given, in terms of omega, in terms of VF, and so on. So in that case, the speed of the bullet, which I'm going to call VB, this is the speed of the bullet after the collision. This would be, well, if it wasn't spinning, it would just be the center of mass velocity. So it's VF plus how fast it's spinning relative to the center of mass. So because it's spinning this way, it gets an extra kick from the rotation. We're solving for things like the speed at which it spins, how fast the rod is moving. We're just trying to analyze the system, basically. Right, I mean, bullet hits the rod, something's going to happen. We should be able to figure out what happens after the bullet hits the rod. And it turns out you need angular momentum and translational momentum conservation to do that. But for now, I'm just writing the bullet's final speed in terms of the variables that we're interested in, like the angular speed and like the center of mass speed. So the bullet is moving faster than the center of mass because it's also rotating, right? It gets an extra kick. And we can relate that to the angular speed by just noting that it's rotating at some rate around the center of mass. And we know the distance that it is from the center of mass. It's 1 minus b times L, and we know the rate at which it's rotating around. So we just add them. So here we have 1 minus b times L omega. This is that v equals r omega. Again, this term accounts for that one. And then the whole thing is moving as well. So that's going to be the speed of the bullet. After the collision. Now, let's just start setting up our equations. So the initial angular momentum of the bullet initial, is, well, it's just a point particle. It's the exact same picture here. It's just now the pivot point that we're using to find our angular momentum is at a different place. We're not interested in the angular momentum relative to the top of the rod. We're interested in the angular momentum, relative to the center of mass of the rod. So the distance that we multiply our momentum by, the r in r cross p, is this distance here, the distance from the pivot point. So here, the initial angular momentum of the bullet is m1 vi times 1 minus bl. Remember that this is mv r perpendicular, right? R perpendicular is the distance from the pivot point to the line formed by the velocity vector. So that's what I'm writing here. Okay, what about the angular momentum of the bullet after the collision? Well, it's the same formula. It's just we have a different speed. In this case, it's m1 vb times 1 minus bl. And then the angular momentum of the rod after the collision would be I times omega. It's I rod times omega. Now we're going to write the moment of inertia about the center of mass, again, in terms of this variable beta. I'm going to call it beta prime though, just so it's not confusing because we already used beta. So beta prime, so the moment of inertia here will be beta prime ml squared times omega. And so beta prime, by the way, the reason I called it beta prime is because we're finding the moment of inertia for the same rod, but about a different pivot point. This would be like the center of mass beta. So in this case, beta prime equals 1/12 if the rod is uniform. Again, it's just a number, and it'll be different depending on how the mass is distributed. And we'll plug in numbers at the end, but I just wanted to do this for a general rod first. Okay. So then, if we set the initial angular momentum equal to the final angular momentum, we get the following equation. We get m1 vi 1 minus b times l equals m1 times vf plus 1 minus b times l omega times 1 minus alpha l. So what I did is I substituted in vb into our equation for the final angular momentum of the bullet. I know this is getting messy, by the way. This is going to be the worst algebra you've ever seen. Plus beta prime times m2 times L squared omega. So that is one of our equations. That is our first equation. That is our angular momentum conservation equation. Then we can do the same thing for our translational momentum. So the initial translational momentum in the x direction is the same as the final. So the initial translational momentum in the x direction, alpha came from here, because we're interested in the distance that the bullet is from the pivot point, not the distance that the bullet is from the end. So that's why, sorry, that's not an alpha, that's a B. I just have alpha in my notes, my bad. Because I forgot that it might be confusing. You might think of it as angular acceleration. Right, so the initial translational momentum is just the translational momentum of the bullet. It's just m1 vi, right? The final translational momentum would just be m1 times vb, speed of the bullet times the mass, plus whatever the translational momentum is of the rod. It would just be the mass of the rod times its center of mass velocity. So it's just m2 times vf. Okay, so then the momentum conservation equation becomes m1 vi equals m1 vf plus 1 minus b L omega plus m2 vf. All right, two equations, in principle, two variables. And so what are we left with? So by the way, all of the variables that I'm talking about, assume everything is given except the final speed, or the final angular speed and the final velocity, which is just to say alpha is just a number that you would compute based off of the properties of the rod. Beta is the same thing. VI would be like the initial conditions that you'd be given. L is just the length. All of those things we're assuming are just like, it's just data that you already know about the system. And we're trying to predict what happens after the collision. That's why I say there are only two unknowns, the omega and VF. So we have two equations. In principle, two unknowns, assuming everything else, assuming you just know you're given everything else, you measure it or whatever. So we could just solve for VF and omega. I'm not going to do that by hand because it's messy. Instead, I'm just going to tell you what the answer is, and you can go home and verify my algebra. So the end result from these two equations is the following, and the end result really isn't pretty. VF equals beta m1 vi divided by 1 plus alpha, not alpha, 1 plus b squared minus 2b plus beta prime times m1 plus beta prime times m2. That is the final velocity. And then the final angular velocity, that's the final translational speed. The final angular speed is 1 minus b times m1 vi divided by L times 1 plus b squared minus 2b plus beta prime m1 plus beta prime m2. So these are the answers that you get from doing the algebra. I told you the algebra is not nice, and the answers certainly aren't nice. But this is just, but this is basically the answer for what happens if a bullet hits some arbitrary rod at the bottom of the rod floating in free space. This answers all of the questions because the distribution and the length of the rod, like the distribution of mass and the length of the rod, are all taken into account in this formula. So we can just plug in and see these things drop out just to get answers. So for example, if the mass of the rod and the mass of the bullet were the same, and the rod is uniform, if the rod is uniform, so that in this case, B is still 1/2, i.e. the center of mass is halfway down the rod, and beta prime, this is the number that's in front of ml squared for a uniform rod about its center of mass. This would be 1/12. Then we can just plug those in and see what happens. And so what we end up with is that the final speed of the center of mass of the system, or sorry, the center of mass of the rod, not the center of mass of the system, is VI over 5. And the final angular speed, the rate at which the rod rotates, is 6 VI over 5L, sorry. And Those are the answers. Like, so now, if you were given a bullet and a rod, both with the same mass, you fired the bullet at the rod was uniformly dense, and so on. If you knew the initial speed of the bullet, you knew the length of the rod, this would be precisely what you would expect the center of mass of the rod to be the speed the center of mass of the rod to be moving at, and this is the rate at which it would be rotating. So, like, you know, I said at the very beginning of the quarter, physics is about predicting the future. This literally lets you predict the future with math, right? Like, you can predict what would happen to the system given some initial information. Can't do that in a whole lot of other sciences, right? So I'm going to leave it as an exercise to you guys to figure out how much energy is lost to the thermal energy here, because this is a totally inelastic collision, right? The bullet is moving with the rod, like they're stuck together. So this is a totally inelastic collision. And so there should be some energy lost to thermal energy. You guys can go home and figure out how much. What if the rod and bullet are tiny? What do you mean? Okay, so I'm going to, so that's the end of angular momentum, or at least it's the end of angular momentum conservation and things like that. We're going to change gears completely now. Turns out angular momentum conservation will be useful later, but we might not get there because there's only like 2 lectures after this one. Oh yeah, no, that makes things tough, but we can talk about it after lecture if you want. We're going to talk about gravity, my favorite subject. So there's a few questions that we might have when talking about gravity. Let's write them down. So we all, like, we're not Newton, or we're not from before Newton. Like, we know that gravity is like what makes the Earth go around the sun. We know that gravity is what makes apples fall from the tree. But we still would have some reasonable questions. For example, why is the force of gravity, or why does the force of gravity have a magnitude equal to mg? Like, why is that the case? It didn't have to be that, right? The force of, like, the elastic force is minus kx. Why is the force of gravity mg? Second question, how does whatever explanation that we have for the first question, how does that relate to gravity making the planets move? Like, how is that at all related to the thing that makes the planets orbit the sun? Last question is, how does gravity work? Lucas, that's a hard question to answer, because presumably, like, with my knowledge now, I could go back and revolutionize physics, but I feel like I wouldn't know as much as I would as I do now if I was 350 years ago. Anyway, so 2 of these 3 questions are easy to answer. The first 2. The third question, we still don't quite know the answer, and by we I mean scientists. I mean, we have an idea, but, you know, still not quite sure. Anyway, so the answer to the first 2 is Newton's law of universal gravitation. You can name stuff after yourself today. You just have to discover it. So Newton's law of universal gravitation is basically a set of empirical observations that Newton came up with. First observation is that gravity is a force that acts between, or this is rather an assumption, that gravity is a force that acts between 2 objects. Okay, all forces act between 2 objects. Fine. Second, gravity is always attractive. You know, I do gravity for a living. Like, I do general relativity stuff. And my wife says I'm married to my work. I'm glad gravity is so attractive. Anyway, that was terrible. I'm sorry. Yeah, no, that was really bad. Second thing, or third thing rather, is the magnitude of the gravitational force depends on only 2 things. You don't get extra credit if you say that was good. You lose credit if you say that was good. I know it was bad. So one of the things it depends on is the mass of the objects. So if the mass of the objects are different, then the gravitational force between those objects will be different. Second thing is the distance between the objects. And in particular, it's not just like, oh, if they're further away, then something happens. We actually know exactly how the distance relates to the magnitudes. It's by an inverse square, and I'll explain what that means in a minute. So we can find consequences of these observations. The consequences are as follows. So first, this is to say, gravity is a force between two objects. So if the Earth pulls on an apple with a force of 500 newtons, then the apple pulls back on the Earth with a force of 500 newtons from Newton's third law. But really, more mathematically, we can combine these results. So the force of gravity should be proportional to the product of the masses of the two objects, m1 and m2. That is, if you double the mass of one of the objects, the force of gravity between them doubles. If you double the mass of both objects, the force between them quadruples. Also, we know that the force of gravity, or rather the magnitude of the force of gravity, decreases as distance increases, and it decreases as the square. This is the idea of an inverse square law. So if you double the distance between the two objects, the force goes down by a factor of 4. If you triple the distance, the force goes down by a factor of 9. That is, the magnitude of the gravitational force goes as 1 over r squared, where r is the distance between them. So we can combine these, or we can combine these formula. We can get that the force of gravity is proportional to m1 times m2 divided by r squared. Now that's assuming there's nothing else that affects the force of gravity, and as far as we can tell, at least from Newton's perspective, that is just it. The last thing to do is to change this proportionality into an equality. Proportionality just means that if you multiply the thing on the right by a particular number, then you'll get the thing on the left. And so we can just measure that particular number. Precisely, it's big G. So we get that so putting this all together, we get that the force of, or the magnitude of the force of gravity is big G times m1, m2 divided by r squared. And big G, now it's just a number. Well, it's a number with units. G is 6.67 times 10 to the minus 11th power Newton meters squared per kilogram squared. That's what it is. It's just a measured number. It's just a number that characterizes our universe. I think that gravitational, so Newton invented calculus, and I feel like calculus was probably necessary for Coulomb's law. My guess is that Coulomb's law stole from gravity. But, you know, they've both been around for 13.5 billion years, give or take a few hundred million, so who knows? Right. So that's great. That tells us what the magnitude is. We also know something about the direction, right? The fact that gravity is attractive tells us what direction the force is. So we can characterize that formally using vectors. And so because it's attractive, it means the force on one object from the second or from a second object points from the first object to the center of mass of the second object. It points to the center of mass of the attracting object. So let's consider for a moment just a quick example. Let's say that we put the source of our gravity, maybe it's the Earth, at the origin. So here we have a plot. We have our source of gravity. Now, in principle, both objects are going to pull on each other equally, but we're going to imagine that the source of that one of the objects is fixed in space. So if the second object is over here, call that, say, the recipient to the gravitational force, then the vector that points from the first object to the second object, the unit vector that points in that direction is r hat. So the direction that the gravitational force would be in would be this way, right? In particular, it's in the negative r hat direction. Come on, scroll, please. So in this coordinate system, the force of gravity rather, in the negative r hat direction. So putting this all together, we can have a vector equation for the force of gravity. The force of gravity as a vector is minus, well, actually, let me put it the other way. It's g m1 m2 divided by r squared times minus r hat. So that is our force of gravity. And you'll usually see this minus sign moved up front, but it doesn't matter where it is. So I'm just gonna, I have like one more thing to say, and then we'll call it a day. So the calculation that we just did, r hat represents the vector. It's this vector. It's the unit vector that points from the source to the recipient. So all of this stuff that we just talked about only applies to point masses. So the question then is how do we handle the gravitational forces on actual real world objects? Like, you have a pen and you have a basketball. What's the gravitational force between them? Turns out that dealing with general extended rigid bodies is hard and requires calculus. Like it's doable, but it's messy. So there is one exception, and that is that for spherically symmetric objects, gravity acts as if all of the mass was at the center of mass. So if all of the mass were at the center of mass and the object is treated as if it were a point mass. So for spherically symmetric objects, these are things like planets, for example, would be a good example of spherically symmetric object. Rather than imagining like a whole big thing, you just treat it as if all of its mass were concentrated down to a single point at the center. It's symmetric as in density, right? Like if the density is lumpy, like the shape doesn't matter. It's just where the mass is, right? So for example, the sun and the Earth are both approximately spherical. And I say approximately, one of them is an oblate spheroid, for example. Approximately spherically symmetric, rather. So it's a decent approximation. So if we wanted to find the force of gravity between the sun and the Earth, what we would do is, we would draw our sun, we would draw our Earth, but we wouldn't use this distance. Right, that's not the distance that we would use. We would use the distance between the center of masses. Yes, certainly not the scale. Here's the sun, here's the Earth. We would use the distance between their center of masses. That distance would be the distance r that we would have to use. So that finishes or that doesn't finish our story. We haven't answered the question how this force of gravity that we just derived relates to F equals mg, which we will get to next time. But I'll leave you on a cliffhanger, and I will end lecture here. So